Okay, hello, I'm Shriram. I'm amazed that you're all here on a holiday, so I am deeply grateful to you. Hopefully you'll find your time was well spent, and if not, you can yell at me afterwards. Um, I'm also super excited, and I'm from Bangalore. This is my hometown. When I was growing up in Bangalore, there was like one compilers person in the entire city. He was some professor at ISC that you couldn't even approach, or you had like, take your chappals off before you went to talk to him or something like that. And now this is here. And this is just so wonderful to see. Like, there's not only like you reach out, it's like, wow, there's an LLVM meetup, and then they'll show up to attend a talk on a holiday. So it's just great that like Bangalore has a compilers community. I'm just super, super excited. This is not going to be like a very technical talk. The talk title onward, I promise, I've advertised. It's not going to be a very technical talk. I am not going to give you details of like LLVM bytecodes and stuff. If I have any questions, I know whom to ask, but I don't have any questions about it either, which you're welcome to, you can quiz me. You'll find that I'll fail pretty miserably. What I want to do is I want to instead tell you about a different side of programming languages that a lot of people don't think about, or people who don't think about in this kind of way. Okay. All right. So I'm sure by the way, by the way, thank you. Who are the organizers? The two of you and who else? Yeah.
And me.
Yeah, great. Okay, thanks. These people have been phenomenal organizers. So thank you for all of your work. You said like there'll be a question and then Q&A. I don't believe in that. Whenever you have a question, just yell out the question. If raise your hand. If I don't see your hand raised, just yell and say hello. And here, okay? So that's the style I prefer to go with, yeah. Okay, so the thing I want you to understand is that I am focused heavily in this talk on working with students. Students are learners. They're a very different population than anybody in this room. The very fact that you're here at an LLVM meetup means that you are already like out there and like, the 1% of programmers. Okay, whereas these people, learners, are typically at the other end, and a good working assumption is that they're somehow a vulnerable population. If they have a bad experience, they will not learn, they will walk away completely, right? And so that is a very different frame of mind when you're thinking about them. Another issue that has become very relevant is people are starting to do computing in primary schools. In this talk, I will not take a position on whether this is a good idea or not. You can talk to me about that later. But the point is people are starting to do this from much younger ages. Okay? So a lot of the computing technology we have was developed by, I don't know, like Niklas Pyret or somebody like that, for people who are already in college in like, Zurich or something, right? Whereas now we have like, literally millions and millions of children all over the world being trained by people who are not going to win a Turing Award, right? So that's a very different kind of audience. And finally, this is something that's very personally interesting to me, is that computing is now being used to teach other disciplines. So I'm one of the leaders of this project called Bootstrap, and we have a project to teach math, a project to teach physics, a project to teach statistics. We work with history, we work with civics teachers, okay? And now that's a very different population that students are coming to learn computer science. Okay, so a computer science student, you can say, look, you're here, you have to learn for loops. I'm like, fine, I have to learn for loops, right? If you go to like a physics teacher or a civics teacher and say you have to learn for loops, they're like, get the hell out of my face. Okay, so that changes everything. Okay, now here is my thesis statement for this talk and also generally for my research. Okay, is that when you think about computing education as a topic and take it seriously in its own right, first of all, it raises lots of significant challenges that require the kind of skills that we in this room have. Even better, some of those problems, not all of them, but some of those problems also lead to technical insights that you can then feed back into more general computer science areas. Okay, and I'll try to show you some examples of this as we go along today. Okay. So my experience is since about 1995, I've been working on languages and programming environments, IDEs, like called Dr. Racket, used to be called Dr. Scheme, WeScheme, Pyret, and so on, and some others. So this is sort of like I'm trying to distill some idea lessons that I've learned from, about 30 years. And at the end of this, you're like 30 years and this is all you learned. Well, I'm slow. What can I do? Okay. So mainly I'm going to have 4 parts to this talk, and we'll dive into each of them. Okay, good. Now, can people see the slides? Let's go through logistics. Can you hear me clearly? Am I speaking too fast, et cetera, et cetera? Okay, so far so good? Okay, back row, raise your hands. Back row, raise your hands. Okay, that means you can hear me. Okay, good? Okay, so if you need anything, just interrupt, okay? I don't know, is it too bright on that screen? Is it readable?
It's fine, yes, it's fine.
Perfect. Okay, so let's start. Here is a screenshot from Dr. Racket, okay? So this student has written a Celsius to Fahrenheit function. And what they have done is Racket has a prefix syntax. And instead, they have written temp times 9.5 instead of star temp 9.5, 905. Okay, now you're like, well, that's a stupid syntax. Well, I disagree with you. It doesn't matter. The point is people make these kinds of syntactic errors in whatever programming language, they make some analogous error. Okay, and now let's look at the error message that they get. The error message says application, not a procedure. Expected a procedure that can be applied to arguments given 100. Okay, now we in this room understand what's going on. We've passed this function 100 as a parameter. 100 has gone into the function position. 100 is not a function. It's saying that's not a function. Okay. This error message is almost indecipherable to a beginner. There's like at least a half dozen things wrong with this error message for a beginner. And I'll actually talk about error messages. That'll actually be a chunk of the talk.
So I think part of the reason
this is modeling good behavior, right? Which is having a question. Go.
I think part of the problem is it's not statically typed, so temp is recognized as a
There's
procedure.
static typing, and then of course we can talk about errors that are caused by static typing that nobody can understand also, right? Right, exactly. So it's not statically typed, so that is one possibility. Okay. All right, so that's not the only error message Dr. Racket gives. Dr. Racket can also be asked to give a very different error message, which says, look, this is a function call. I expect to see a function after the opening parenthesis, but I found a variable instead. Same program, completely different output. Okay, now, like, what's going on? Well, the key thing is there's a thing that says language colon, and one of them says Racket, which is this full-blown, ginormous language, 1,000-page manual. You drop it on your foot, you'll fracture your foot, that kind of thing. And then the lower message says beginning student. Okay, so what's going on is there's a broader principle here, right? So you take any programming textbook. Okay, so this is mine, but you can have a different one that you like. That's fine. The key thing is any programming book you take for any programming language will always start with a small bit of the language, and then it'll grow the language, and it'll grow the language and grow the language, and keeps growing the language as you go along. And even by the end of it, it will rarely ever get to the full language, right? There is no C++ book in the world. Like, I don't know if even the C++ manual covers the full language, never mind any introductory programming book. Intro Java books will never cover all of Java. Intro Python books will never cover all of Python. So no book ever covers the whole language. It always picks some sub-language, says this is the same sub-language for the thing I'm trying to teach you. So the question we asked back in 1995 was, why doesn't the IDE do the same thing? Right? Because what people say, like, well, we are going to program in the sub-language of the full language. Yeah, but if the IDE doesn't know that and doesn't give you error messages, et cetera, that match up with that sub-language, the beginner is basically hosed. All it takes is one typo, right? Like we saw, one typo, and beginners, of course, make mistakes. That's why they are beginners, okay? So we coined this concept of what we call language levels. Lots of things happen in a language level. You remove some features, you limit some other features, you modify the error messages, you give different tools, et cetera, et cetera. Okay, so basically you give this beginner a sense that this is the whole universe, and then you keep growing the universe as they go along. Okay, that's the idea. Now, technologically, there's a problem, right? Because you need to build n different languages now. It's hard, as everybody in this room knows, it's hard enough to maintain one language. Now we have to maintain n languages, okay? Well, okay, so I can tell you what we did initially in Dr. Racket. We built one language and put some flags in it, okay? Oh, there's flags, and there's flags, and there's many, 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 many flags, right? Enough flags that at some point you start asking yourself, maybe there is a more principled thing we could be doing here. What we really should be doing is rethinking what our notions of modularity are. So we have lots of notions of modularity in our programming languages, right? I mean, you know, depending on your favorite language, it's got like subroutines, it's got objects, it's got classes, you know, et cetera, et cetera. We have lots of different modularity mechanisms. So we said, look, we think there's actually one more modularity mechanism, which is the notion of a language. The notion of a language is also a kind of module, okay? And you want to compose languages just as you compose other things, like you compose objects or you compose modules. Okay? And so there's a broader principle here I want to enunciate, which is there's a sense I have that when you make an operation really cheap, it changes the way you think about it, right? One of my favorite examples of this is actually completely unrelated to PL, which is you think about like TCP/IP, right? If you think about TCP/IP, IP is like no guarantees at all, right? Effectively, no guarantee. You send a packet, like, okay, something happens, right? That's it. You sent a packet. That's the only guarantee that a packet has been maybe sent, right? But it's so cheap, so dirt cheap, that you can actually build entire reliable protocols on top of it, like TCP, just by the idea of being able to resend packets often enough. Okay? If you think about objects, same sort of thing happens. And this is something that I actually learned from Joe Armstrong, right? Joe Armstrong pointed out, like, when you program in a language which is sort of object-oriented, what does that mean? You can create as many objects as you want. You don't think of it as a really expensive operation, right? In fact, when Java first came out and made objects expensive, it was like, oh God, now I have to think about how many objects I have, right? But if you make object allocation really cheap, you can program, it changes the way you think about your program. And Joe pointed out in the context of Erlang, in the context of concurrency, he's like, look, threads are so expensive, we do thread pools. What is thread pools? That is an utter failure of a language design, right? Like, you have object pools. I will allocate 100 objects and just reuse them as I go along. That's crazy. You can't program that way, right? So X-oriented programming, I like to say, is X is so cheap to use that you stop thinking about its cost and you just like develop entirely new ways of programming because X is so cheap. Okay, and thanks to Joe for the insight that led to this view. And so what we do is what we call language-oriented programming. Make the act of creating a language incredibly cheap, right? So technically, what we do is we enrich this idea of what import does. Normally, import in most of the languages you program in, imports like, objects and functions, classes, things like that, right? We said, what if import also imports pieces of a language, right? So you can bring together pieces of a language and compose them, just like you can bring together functions and compose them, you can bring together objects, right? So normally import will provide, like names bound to various things. For us, import also brings in language extensions, language restrictions, closing over libraries, and all kinds of other type information and so on are all part of the import mechanism now, right? You don't need to say, oh, I have a new kind of first order thing in my language that needs a new import. Import and Racket can import all of those things. Okay.
How is it different from, let's say, you have a compiler flag, then you enable the compiler feature, like let's say the standard versions, right?
Yeah.
You have standard 11, 14, 17, and 20. In each version, you enable the language feature, right?
Right. So the idea is all of that goes away, right? Like that, the notion of a flag means I have this combinatorial blow up, right? I can't compose flags. I know how to compose functions. I don't know how to compose flags. So we said, why can't you compose language features the same way you compose functions rather than non-composable flags? Okay. So I'm not going into the full technical details. This is like a talk and a half, right, to go into the details. But I want to point out also, all of you already live in this universe, right? Anybody who ever writes front-end code, almost nobody programs in JavaScript, right? You always program in some like super sub-language of JavaScript, right? But, or, if you're like an academic, you might like, oh, you got tech, but then you build LaTeX on top of that, and you create ticks on top of that, and you create circuit ticks on top of that, right? We're always doing this. We are linguistic beings, not only in our natural language, but also in our programming language. We can't help but invent languages, right? But we do this in this incredibly ad hoc, brittle way. We're like Stone Age people in the way we create languages, right? It's ad hoc, it's brittle, we don't have good mechanisms for composition. So everything's kind of broken, right? You compose this thing and that thing, it sort of works, and sometimes it doesn't work. And then you post to Stack Overflow and they're like, you can't use those two packages together. Then you copy the package, you change all the names in the package, and you do it. Then you have a fork, and then you maintain the fork. This is bullshit, right? So the idea is it's the right principle, we just have the wrong mechanisms. And Racket's idea was, we'll just give you the right mechanisms.
Yeah, so there's this concept of teaching languages, right? Like languages.
Right, that's that.
Yeah. So like, how is this approach of having a language that's gradually unveiled to you better than just starting with a teaching language and then shifting the student to another language?
Because of the shift. The shift is a non-trivial problem, right? In this book, right? Imagine that for those who can. So imagine if you started like this part was Scratch, and then this part was Python, and then this part was, Java and C++. Your students will all, basically what will happen is you'll start with 100 students, right? You'll be left with 10 amazing students, right? These are the next LLVM hackers, right? Everybody else will be like, this is bullshit. This is no way to teach anything, right? I mean, imagine if you did that in a physics textbook, right? Imagine if your physics textbook started out on day 1, we'll use this, and then day 2, we'll use that, and day 3, we'll use this, day 4, use that. You're like, this is not a pedagogic principle at all, right? Our point is, you can make your own teaching languages, right? You can carve your large language down into your own teaching language. You don't have to invent a teaching language that then stops working at some point, right? So there's this principle that Seymour Papert talked about. He talked about low floors and high ceilings. Low floor means it's very easy to get into. High ceiling means it grows a long ways, right? Teaching languages give you low floors. And then like the moment you stand up, you bump your head and like you get a headache, right? Okay. Now, the other thing is each person has their own textbook, right? Every textbook author has their own philosophy of how to break down a topic, right? So these languages go with the textbook called How to Design Programs, and it's one particular way of decomposing the problem. But, we have friends in Germany who have their own book. It's called Dein Programm is the name of their program. Gemachte Abstraktion is the name of the textbook. They have a completely different way of decomposing the world, right? So if the only thing that Racket provided was our view of the world, then it doesn't work so well for their book. But they have their own view of the world. Because we have this principle of languages, they can break down the language in whatever way they want. And so that's why you get this selection of languages instead, right? And and then you can generalize from that. And so we have experimental languages, we have new research languages, all these other things, right? And then the way we grew this out was to say, well, you can have typed Racket, right? And so the key thing here is the first line of your program says #lang. #lang basically is, if you've ever written a shell script and you've done a shebang in a shell script, this is shebang for adults, right? It basically says, this first line is going to dictate how the rest of the file is interpreted, both semantics and syntax. Okay, so this language looks an awful lot like Racket, parentheses and stuff like that. It just happens to add types. But then this is a language that I built called Margrave, which is for dealing with, we do security policy analyses, network policy analyses, and so on, differential analyses, and so on. So it looks vaguely sort of SQL-ish. Right? And its semantics is entirely in terms of SAT solving, right? So it's neither the syntax nor semantics is Racket. And then, Scribble is how I write my books. And so Scribble is basically a language for writing documents. It's a markup language, right? It's got like #bold, right? This is actually a Racket program. All this turns into a giant big Racket program. And you get all the benefits of like separate compilation for books, just like you do get for software, right? But the point is, you get all these languages. So once you open up the idea of languages as modularity mechanisms, then Racket disappears as a programming language, becomes a platform on top of which you can build whatever languages you want, including things that are like text processing languages that have nothing to do with programming languages. Right? So, and there's like over 100, like Naughty Dog uses it at work. So we have like commercial uses as well because it liberates new ideas.
All these are derived from some grand language? Or?
No, they're all independent languages. They just happen to run on the same platform. What the platform provides as a service is the ability to create your own language.
But where is this sub-moduling or sub-languaging coming to picture?
So these are whole languages. These aren't even sub-languages, right? These are complete programming languages. That's the point. We started off with this idea of, I want to create sub-languages.
Right.
I'll do that by adding command line flags. We said that's a really ad hoc thing to do.
Yeah.
We'll break out this general principle of defining languages. And once we generalize the principle enough, you can make languages that look nothing like the original, right? There's a data log language, for example, right? It has the syntax of data log and the semantics of data log. All of them, the only thing that that Racket provides is the common substrate, right? So think like JVM, okay? So JVM is useful because you can create both, you can run Java, but you can run Clojure on it, okay? Racket is the same way, except the key thing that JVM doesn't provide and like Erlang's VM doesn't provide is this #lang mechanism.
Okay.
Right? #lang mechanism is baked into the VM. And so when you say hash, it expects to see #lang at the top of every file, and it knows what #lang means. It knows how to retrieve languages, how to compile them, how to run them, how to manage the runtime, and so on. That's the service it provides.
But so composition also possible? I mean,
yeah, I haven't talked about the composition here because that would be a whole talk in itself. It is possible, and I can show you some good examples, but also some bad places where it breaks down in funny ways.
Okay.
But adding that has interpretation, that has some disadvantage, right?
Sorry, adding what?
It has like the has
Hashlang. Uh-huh.
some of the interpretation, it has some disadvantages. That's why the Java don't have this.
What do you mean by disadvantage?
Java don't have that the has then land or inform like how the self interprets, right?
Yeah.
Any language how it interprets, but the Java don't have because of there are some disadvantages.
Yeah, I know. What are the disadvantages you're referring to?
There are a lot of disadvantages because you are interpreting the language.
No. Sorry. When I say interpret, I don't mean interpret in the sense of an interpreter. Interpret means this. Each of these is actually a compiler. These honest to goodness compilers. They're not interpreters. Okay. When I say interpret, I'm using it in the English sense of saying give meaning to. That's all. These are honest to goodness compilers. Okay. In fact, typed Racket runs much faster than Racket because it basically the compiler uses the type information to compile that Racket can't use. So these aren't interpreters. Okay. You could write one if you wanted to, but they're not. None of these actually are. Does that make sense? Yeah.
So you can basically create your own hashlang also, right?
Exactly.
So when you define your own hashlang, you will have to define everything from lexical analysis to everything, right?
You can. So I do this, for example, in my programming languages class, we use about 35 different hashlangs. Okay, so I have this approach that I call the mystery language approach. So the mystery language approach is basically I give you a program, I give you a language, I give you a syntax, you write a program, and each program produces like 3 answers. And you have to write programs to tell apart how the answers are being computed. We can talk about that later. So the point is you get for default a bunch of readers. So if you want parenthetical syntax, you get that for free. Okay. If you want like a particular kind of infix syntax, we give you that for free. There's now a new syntax called rhombus. Okay. So there's a bunch of syntaxes automatically built in. So if you're happy with one of those syntaxes, you don't have to do any of the lexical analysis. You just define the runtime semantics. That's all.
So you are basically making it easy to create compiler.
So Matthew Flatt has a great quote. His quote is that macros are a lightweight API for compilers. Right? You want lightweight APIs for compilers.
That's also true in the case of Rust, which also has a very robust macro system where you can define your own language syntax.
Guess whose macro system it's based on?
But everyone, if he creates a language, then that is a problem, right?
Sorry?
Because everyone wants to create a language, but it is problem for the whole world. Because of which language you will first start reading.
I'm not going to get into the philosophical discussion about that. I'm trying to find a repo and I'm having some trouble finding it. Hold on. GitHub mystery.
The answer to that question is COBOL was the best language.
There you go.
COBOL
Was the best language.
I can pass. I fully support that.
Yeah, here we go. So like here is here. So I don't expect you to read this, but this is basically a language extension that all it does is it modifies the way field lookup works. Okay, and the entire thing is like 30 lines of code, including some boilerplate and stuff like that. And in fact, the whole thing is really actually, you can ignore the multi-runner. It's really just, it's like the mod begin does half the work and then the other half the work is in one other file, right? So the idea is we want to make it really, really easy for you to do this kind of language extension.
The purpose of Racket is to make it easy to create custom language.
Exactly. Language-oriented programming, right? X-oriented programming means X is so cheap and easy to do that you will make lots of X's.
Okay.
Language-oriented programming is, we're going to make it cheap and easy to do lots of languages. Okay. Good. Yes.
So how do you define the base subset of Racket? Like, is it like it should be Turing complete or?
Yeah. So Racket itself is a Turing complete language. I mean, you could think of it as like, think of it as like LLVM or JVM or any of those things, right? It's similar enough.
Okay. Yeah. But so the features you define on top of that, how do you say that this should not be a part of the minimum subset that a language should provide?
Because when I say hashlang, I get to define the entire universe.
Mm-hmm.
If I want to, I can say I'm extending an existing language with something. Okay. I have a cute extension, for example, where here, I'll just show you the extension. And I don't even have to explain it then. So here is here is a programming language that looks pretty normal, except I can write Roman numerals in it.
Okay.
So I've taken Racket and extended it with Roman numerals. Okay, so that is a language extension. Okay, but in contrast, when I say hash lang, I define everything. So in hash lang scribble, for example, I basically said the syntax of the language is this markup kind of language, and the semantics is basically it just generates HTML and PDF. Okay, so I can define sub-Turing languages because I get to define everything.
Yeah.
So data log, for example, is a sub-Turing language. If I say hash lang data log, I cannot write an infinite loop in that. Or if I have simply that lambda calculus, right? So it gives you the mechanism to either incorporate new features into the language or just define the entire language
And
from.
also subtract features, or you can.
That's right. It's subtraction is a little tricky because subtraction is hard. We don't do subtraction as a native thing. If you want to do subtraction, you say, I'm going to start from the base and build up by adding everything except something.
Okay.
You can import, you can say, I want all of Racket except this thing. That's how you do subtraction.
Okay.
Okay, but for technical reasons, it's done that way rather than remove something. Because if you remove something, like if the program already refers to it, what does it mean? It gets complicated.
Yeah.
Does that make sense?
Yeah.
Okay.
Have you tried creating DSLs out of hash lang?
Oh God, yeah. I mean, hundreds. Yeah.
So is there any external support for doing things like scheduling or basically?
So the Racket VM gives you a lot of that, right? So that's part of the runtime system. So the Racket VM will give you like threads and all the, it gives you threads. It gives you like actor-based models and things like that if you want to do that sort of thing. There's a whole lot more to this that I'm not really going into because it's what meant to be a Racket talk. Because this was meant to be about student languages, right? Because there's also resource management is a very interesting problem, right? Because I have these resources now between languages, right? It's like really you've turned everything is a language interop question, right? So you also need the ability to language interop. So if I've typed an untyped program, what does interop mean between these? These are all like very interesting, subtle semantic questions. So not quite the focus of the talk, but I'm happy to talk more about it later on. Does that make sense?
Yeah.
Okay, so if you want to read more, this paper is a pretty good introduction to it. And I just want to point out, like this the round trip thing I was talking about, right? We started off with this very basic question of like, how do I make my IDE look more like my textbook and grow like my textbook? And we've gone from that to this entire hash lang concept, which is now a general principle that, if you like, it's a general principle that is now well enough explained in scientific literature that you could imagine other VMs doing this too. There's nothing about Racket specifically that needs to do this, right? Other VMs could do this. And, like the next JVM could easily do this and provide first-class support for things like Clojure rather than it having to be the sort of hack on top of the JVM. Right? Okay. So that's the first part of the talk. I want to talk a little bit about runtime systems now. Okay. So let's start with this. I'm going to give you a little quiz. All right. So here's the quiz. I'm going to write, imagine whatever your favorite language is, right? I have some overlay function that overlays images, and I'm going to take this Thunderbolt image and overlay it on this cloud image. Okay? Yes? What do you expect to see?
Cloud with Thunderbolt on it.
Cloud with Thunderbolt on it? Cloud Thunderbolt on it? Yes, everyone okay with that? Yeah? Okay, good. So here's some JavaScript code if you like, right? So I have an image and I say, image source is whatever the Thunderbolt is, image source, whatever the cloud is, overlay. Yep. Okay, we're good. Everyone good? Yes, good. Okay. And by the way, the reason I'm bringing this up is because this is kind of a really fun exercise to do with beginning students, right? So in particular, in the curricula that I talked about where we try to teach math, we want to teach the notion of function composition, right? The way if your school books were anything like my school books are like f of x is x plus 2, g of x is x squared minus 17. It's like, right? I get the answer is 37. Is that right? Is that wrong? Who knows, right? Whereas you do it this way, and not only do students, they can immediately tell whether they've gotten it wrong. They also deeply care. If they get it wrong, they will like sit there and work for hours to get the composition right, right? So we use this image overlay and image composition as a way of teaching function composition. So it matters that we get this right. Okay, now, historically, here's what this produces, but the one should tell you maybe sometimes you get other answers, right? So sometimes you get this. Okay, or sometimes just silently fails, or sometimes we used to crash Firefox writing this stuff. Okay, what's going on? Well, you can have Stack Overflow, right? And Stack Overflow. How do I make an image load synchronously? It's like, not a problem. It is possible, but only with the ancient art of base 64 and data URLs. This is a very evil way. And then you'd scroll down. Next answer is like, no, it's a non-evil way to load images in JavaScript synchronously. You just have to write this and don't forget to call await everywhere, etc., etc. Oh, it's not really straightforward, right? So now imagine that this is your first week of programming. Okay, who does this retain in computer science, or who does this retain in the course, and who leaves? Right? Okay, so this is not good. Why does this happen? Well, let's step back for a moment, right? I'm going to talk about JavaScript now. Okay, so what we've noticed over the years is like JavaScript, as in the form of Chromebooks, I don't know how much this is true in Indian schools, but certainly in US schools, like Chromebooks have completely taken over. Anyone know what the Indian school situation is, by the way?
At least my kids use Chromebooks.
All Chromebooks. Chromebooks? No. Chromebooks? Not Chromebooks. What do they use?
Just normal laptop.
Well, there's nothing abnormal about a Chromebook.
I think before COVID, they didn't have, at least from my brother, he never used a laptop before.
No, they didn't have a laptop, that's fine. I'm just wondering like whether they are all still, because like schools have realized they don't want the hassle of administering these things.
Yeah,
right?
they write
Like
code
Windows
on
administration.
They write code on paper.
Yeah, that's fine. I learned to write code on paper. I survived, so that's okay. Anyway, so the point is, the browser is like the way to deliver like educational apps, right? And we need it too. All these people, you have browser-based applications, okay? And what's the problem here? Well, you also get things like this, right? I accidentally create an infinite loop. I'm stuck. Please help. I was in the topic using end while under while loops in PHP. I accidentally create an infinite loop. Okay. Even look, bailing out of the console. How do you force the console to quit? I tried Control C. I tried Control X. Doesn't work. Okay. Please help me break out of my infinite loop. I keep crashing my browser. Lol. Right. Okay. Now, of course, we could just say we're going to ban infinite loops. Right? First of all, there's this thing called halting problem, but setting that aside, all the infinite loops are super useful, right? In both the algebra and the physics curriculum, we have students in the algebra curriculum, we have students build and design and run games. In the physics curriculum, they do simulations, okay? Those are fundamentally infinite loops. You take away infinite loops, you take away the whole curriculum. Okay. So what do? Well, here is the fundamental problem, right? It's because JavaScript is a single-threaded language. Right? So it's worth asking, is that a good idea? I think it's actually a fantastic idea. It is one of the best decisions ever made in PL design, right? Because fundamentally, we have these three concepts, right? We've got state, we've got threads, and we've got locks. Okay. If you have threads on their own, great, not a problem, right? In fact, JavaScript does now, right? Like non-interfering threads, not a problem. Okay. If you have state and threads, bad news, right? Had this been what was released, right? Like the entire internet would be deadlocked. Now, it might be great for our productivity, but it wouldn't have been so great for the internet. Okay. Now, state threads and locks, I mean, sure. So look, I live in a city called Providence, and down the hill from Brown is Rhode Island School of Design. I like making fun of them. They're actually amazing designers, like one of the best design schools in the country. Okay, those people know more JavaScript than I do. Okay, but I think if we had told every web designer in the world, you have to understand, like read Morris Herlihy's textbook on like multi-threaded programming, I don't think we would have gotten very much code in the world out there. Okay, even Brendan Mike says this multi-threaded stuff frankly scares me. Right? It's like tough. It's tough to get right. Deadlock, live lock, all these things. So instead, what Brendan did was he said we will have just state, right? Just state, single thread of control. Okay. So that is the state of JavaScript. So now let's say I'm building an IDE that runs in the browser. So I've written some program, I've written some odd even function or something like that. I click run, I start running the program. What happens? Well, I click run, event queue gets a run object, and then it starts running the program. And it says, okay, even of 1000 is odd of 999, even of 998, and now I click the stop button. Okay. Well, JavaScript is single threaded. So that event sits in the event queue, and this continues odd of 997, odd of something keeps going on. You press stop button again, right? It's single threaded, so it's event 432, event, you can mash the stop button and nothing's going to happen, okay? In fact, that stop button won't even like highlight as you hover over it because there's no thread of execution there, nothing, right? Okay, this is JavaScript, okay. Or you can program like this, right? Again, remember, this is stuff we need our first week students to run into. Okay, so it's also not a solution. So here is a broader principle, right? We have these things when we run into these kinds of situations because of our programming languages, it ends up affecting everything, right? There's a burden on the programmer, it interferes with the curriculum, and you get like bad learning experiences. And each of these things like reinforces the other in a negative way, right? These are vicious cycles. I claim that there's a sort of a pedagogic language design principle or pedagogic system design principle, which is the limitations of the medium should not become part of it, right? This single-threadedness of JavaScript is great for us to talk about. It is not the responsibility of the student to have to think about it. Okay? So what could we do instead? Okay, so we're going to run our program. We're going to run our program. We click the stop button. Okay, and after a while, our program should stop. Okay, it should relinquish control. This is, of course, just cooperative multi-threading, basically, right? So I'm using TSR. Is anybody in this room old enough to know what a TSR is? Nobody in this room is old enough to know what a TSR is. Back.
I know what it is, but I don't remember.
Back in the last days, DOS 3.1, there was an operation called terminate but stay resident. There's an interrupt. Basically, when this program stopped, it got wiped out of memory because there wasn't enough memory. TSR means terminate the program, but leave everything still in the memory. Okay, and this was the trick that you use for creating like, you know, background task managers and stuff like that. So we want the program to terminate, but stay a resident, right? So essentially we're going to copy the stack over to the side. Okay, and then we're going to put a resume object into the event queue. And then we point to that and we literally stop. We just terminate the program. Okay, so what happens now? Well, after some time, well, you know, maybe there's other things there, like maybe there's a save file operation or whatever. All these other events can run. In fact, even that stop button can like respond, right, to highlights. And then when we resume the program, we copy the stack back and we can continue running until the next time we interrupt the program. Okay, so I can even show this to you, right? So I've written a little infinite loop here, right? Function that just calls itself. And now I say inf and starts running. And notice that when I hover over the stop, it actually highlights. And I say stop, it stopped. Okay. So that is the execution model that happens inside. This is Pyret. Pyret, WeScheme both do this. So that's the execution model, right? So in fact, it makes programs slow because, you know, we're constantly stopping and restarting the program, but it means the student gets a extremely pleasant work experience, right? They don't have to post on Stack Overflow and say, keep crashing my browser log. Yes.
So how do you decide how often to do the TSR?
That's a great question. Okay, so in fact, we have an adaptive scheme for doing that. So okay, this is a great engineering question. Okay, so there's a trade-off between simplicity of runtime and really good user experience. And sometimes if you get too clever on the user experience, you end up with a crappy user experience. And so sometimes we prefer simplicity. So Pyret basically is about in fact, you can also, while you're starting up your program, you can make some calls and figure out roughly what your platform is doing. Because, you know, this is an M2, but we also run on Chromebooks. We run on like cheap Chromebooks, right? So you can figure out what makes sense. But roughly about every 100 milliseconds or so, you want to yield no more than a second for sure. Because what happens is when I go and do that hover, if it doesn't respond quickly enough, right? So if I do, if it doesn't respond quickly enough, people panic, right? And it's all about making sure that that experience is a good experience. And 100 milliseconds is really good. 250 is fine. 1 second is too long. That answer your question? That's where you're going, right?
But that depends on the user, right? User experience, how.
User experiences always depend on users. That's right. Yeah.
But it differs from the different user for different.
Yeah, I'm not going to start my programming IDE and have them take a survey or anything like that. Yeah, you can. We know enough about human psychology to figure out what makes what works and what doesn't. Okay. Okay. So what I've done, of course, is those of you who know continuations. I've just implemented continuations. I love continuations. My favorite thing in all of programming languages. So don't get me started on it. And once you have continuations, everything is good. Right? We can do graceful termination, we can do long computations, we can do everything, single stepping, et cetera, et cetera, et cetera, et cetera. Right? You just need to implement this one for it. This is also how you solve the image problem, right? You load the image, you do blocking IO for free, so people don't have to. So the actual tech, so again, we're in a PL audience. I'll tell you a little bit about the technical details here, right? So we don't use CPS for continuations. It's far too slow. We have the scheme that we call stack reconstitution. There's a paper on it if you want to read more. If you really want the details, it looks like that. I'm not going to expect you to read that, but there's all the appropriate ICFP compatible Greek symbols are in the paper. So the idea with stack reconstitution is we basically allow programs to run on the regular stack. CPS basically gets rid of the stack. Okay, continuous partition style is we don't use the stack, use only the heap. But that's bad because architectures are optimized for the stack. Also, like debugging information, everything is optimized for the stack. So we run on the stack for a while, and then we basically like create a shadow stack and then reconstitute and like turn that into a data structure. If needed, if you run below the threshold where you're going to do this, where you're going to do the continuation capture, you just do pushes and pops on the stack and you're done, and you never pay any price. So in fact, if you do like shallow recursion in Pyret, it's super fast. If you do deep recursion, then you start paying for the stuff, but it still works. Right? That's the key. There's too many languages out there, so we did this first for Pyret, and then we said, well, but Python IDEs don't get this, and Clojure IDEs don't get this, and so on. So my former student Arjun Goa had this brilliant idea. He's like, why don't we build a JavaScript to JavaScript compiler, right? So there's a system called Stopify, and so Stopify takes JavaScript and creates Stopified JavaScript, right? So you can inject this, and we've done this to about like 11 different languages now. When do you pause is exactly a good question. There's an adaptive scheme that's more dynamic and more clever, or you can just be simplistic and say about 100 milliseconds. And finally, there's a question of like, how do you make sure this sound, right? Because I said JavaScript to JavaScript, and if you've ever studied the semantics of JavaScript, it's like bad news. Here's the interesting thing. We are not trying to modify arbitrary JavaScript. We want to modify the JavaScript that compilers produce, like, Clojure script produces or Foobar script produces, right? So the reality is like JavaScript is a ginormous language. And then there's this nice part of the language that we know how to do very soundly, right? And what we found is that most of these compilers actually go into mostly the good parts, right? So essentially we can optimize, we can fine tune the stopification strategy for the sub-language that the compiler produces. So this is my take on this, right? Is like every sufficiently sophisticated JavaScript program essentially has like continuations done crappily by hand. Right? So Stopify just gives it to you as a primitive operation. Boom, you can write your program, you're going to get stopification, you get continuations for free, then everything else is done. And if you want to look at, there's a nice demo on stopify.org, and you can see, in fact, like you can select there's JavaScript, Dart, Python, Scala, OCaml, C++. There's some, one of the C++ code generators. Okay? So you can take any of these and you can do like simple stepping and stuff like that. Okay, good. So that's the second principle. So language decomposition was the first one. Second principle is runtime systems. I will talk briefly about accessibility. The main accessibility stuff we worked on is working for visual impairment. And I actually feel a very great responsibility for this because, as I said, we have these curricula based on like working with image composition and video games and so on. And that's great, except, for the 10% of students that have some visual impairment, it's not great. For like the 1 to 2% that are blind, they literally can't use the curriculum otherwise, right? And so there's issues with writing code, there's issues with IDE navigation. They're not actually that difficult, they're not that subtle. More interesting thing is when you build a REPL, how do you make the REPL accessible to somebody through a voice interface? Well, it turns out if you talk to blind users, we've spent a lot of time thinking about this because they have chat interfaces. REPL is just another kind of chat. That's all it is, right? So what we do is we adapt the principles from chat interfaces to the REPL context. You have to describe colors, right? So we can talk about that. We got a grant from Vince Cerf. So Vince Cerf gave us a bunch of like Google Cloud data, Google Cloud resources, so that anytime you import an external image, you can basically use like a Google API to describe the image to the user so they have a sense of what is on the screen because they can't see it for themselves. And since we compose images using scene graphs, that's great. We retain enough information and modify the runtime system to retain the scene graph. So when a blind user says, what is this image? It just reads out the scene graph as text in a way that they can understand. And finally, even describing value output is complicated, right? Like 3 versus 3. Right? And there's this principle in the blind, in the blind community that's not related to programming called semantic prioritization. So you say a number 3, the string 3, and there's a word ordering and the way they do it, because also blind users typically go like several hundred words per minute, right? Extremely high frequency. And so you have to basically get all the word ordering right so that things work for them at that frequency, right? So again, if you think about some of these accessibility issues, I'm not going to say much more about it, but it's a really important problem and one that I think we generally have not paid enough attention to, right? And it's like those of you are like, oh, I'm going to introduce kids to Scratch. It's like, great. And how is a blind user going to move a block across a screen? Sometimes. Okay. Last thing I want to talk about. So how long do you guys normally go?
1 hour.
1 hour. Okay. So I could talk for a long time about error messages. I love talking about error messages. So what I'll do is I'll start talking about error messages, and anytime you want, you can just say like, that's quite enough. Okay, good. Okay, let's start with error messages.
Before starting that,
Go. So he's already decided on what this sounds gonna Go.
So yes.
Oh, a question for me. I thought you were going to make an announcement. Sorry. Okay.
So previously, you talked about runtime systems, right? Now you have accessibility features, but how do you tune the runtime? Now it's about speech. No, it's
Not very efficiently. So this is the thing, right? Like every one of the things that I've told you about is yet another way to make programs slow. Okay, and you have to pay a price somewhere. And in our case, we've decided that the user experience is absolutely vital. And so the runtimes. So if I had my druthers, I would basically take like all the scene graph information and bake it into the JavaScript VM. Okay, we don't have that ability to do that. So we maintain dynamic data structures. I'll show you another thing related to error messages that's just like painful, right? So the languages that I build are just fast enough. Okay, they are not blazingly fast. I can't afford blazingly fast because blazingly fast. Basically, think of this as a talk about 4 ways to make your language slower, or 3 ways to make your language slower. Okay, the language levels is a separate thing, but the other thing are all ways to make your language slower, right? And I'm not too embarrassed by that. I'm kind of shameless also. So.
Related question. See,
Yeah.
the first talk, this language engineering, you said we design. Is there a mechanism where we can say port that into faster languages or some kind
Well,
of?
there's nothing slow about them, right? Like Racket is like typically beats Python by about 40x on most things. So if Python's good enough, Racket should be 40 times better, right? So there's nothing slow about that, right? The slowness comes about. No, but let me be clear. The slowness comes about because I need to do continuations and keep halting the program. Or I have to store extra information to give you better error messages. Or I have to store extra information to make it visually accessible. Those are all like features that are nice to have that are not needed, but they're orthogonal to the language level part. Does that make sense?
Yeah. But my question is, I mean, taking the community into consideration, there are not people, say I write a DSL, but I want to put it in a general programming language after I write it into a DSL. I want to move it to a Java or C or some kind.
Totally not my problem.
Okay.
Yeah, no, that is seriously my attitude. It's like you want to use crappy technologies, go right ahead.
Yeah, that's fine.
Yeah. No, I'm being a little sarcastic, and I don't mean to be. It's just that so here's the thing, right? I have half my life as a technologist building the technology, the other half as a scientist writing the papers that explain what's going on, right? Once the papers are written, anybody's welcome to take them and copy them and do whatever they want, right? Like with Stopify, we built this web demo for Stopify so that anybody, like those Python developers who have like web-based Python IDEs, can copy our ideas and put them in theirs. And one of the tech companies that I talked about has actually been looking at using Stopify in their runtime system. But if they don't want to, it's up to them, right? So same way with the language DSL stuff as well. Back there.
Right. So when you were demoing Pyret,
yeah,
you mentioned wanting to avoid continuations because they make too many heap allocations. And you have this thing called stack reconstruction.
No, no. So to be clear, I want to avoid continuation passing style,
right,
which is a particular transformation. Yeah.
And so Pyret, I think transpiles to JavaScript. Right?
Yeah.
Running in the browser. So how do you get to decide what goes on the heap and what goes on the stack if you're transpiling to JavaScript?
Because we just make function calls. I assume function calls go on the stack. So that's my working assumption, right? So so in CPS, everything is a function call. There is no return. Even a return is a function call, right? In our case, function calls are actually like in Stopify, a function call is a function call and a return is a return, right? That's in that sense, we're just using the stack. Okay, does that make sense?
Yeah.
So like if I did like a very shallow bouncy thing that just called and return, called and return, called and return, it would just be calls and returns on the stack and you wouldn't notice any like heap allocation because of that.
Okay.
Yes.
So-
Go ahead.
What are the users exactly that Racket and Pyret are targets basically?
Yeah, so I don't want to, Racket is separate because Racket's own VM, it runs on a desktop, but for Pyret, in some sense, our users are people who want something that is fast enough to get, reasonable animations at about 24 frames a second. So I can build like basic video game type things. I can do my physics simulations. I want, we have a type system, we have algebraic data types, all of that stuff. So I can teach like all of CS1, CS2, streaming, that sort of thing. So basic, like a non-trivial first 2 years of computer science and these kinds of animations. Right? What I can't really support is like massive amounts of data. So we also have a data science curriculum where people work with, tables of several thousand rows, right? Which is plenty enough for the kinds of stuff that we do for teaching basic statistics and basic table manipulations and so on and getting them to understand various principles of data, right? But if you have 1 million data points, Pyret's not going to be good for you, right?
Then why is it the case that, Racket is not much of a herd compared to the other languages, maybe like, for example, I said in maths actually, but I never heard of Racket or anything actually as such.
Yeah.
Mostly heard of MATLAB, Python, and
Right.
maybe Fortran as well.
Sure.
So these languages are mostly that I heard of,
Yeah.
but not of Racket actually as
Yeah.
such. Why do you think that is the case?
Why have people heard? So we know enough from network science to understand how celebrity works, right? It's the Matthew effect. Like famous things become more famous, less famous things don't become more famous. I mean, it's just, I don't know.
You're shying away from something, I guess.
So why?
No, I'm not. I mean, I think look, okay, actually, I'll tell you why. People hate parenthetical syntax. It's really that simple. Okay, which is why, in fact, if you look at Pyret, you'll notice that is not a parenthetical syntax, right? We created Pyret literally to be a non-parenthetical syntax. That was the entire design principle, not parentheses, right? It has to look conventional, right? We have a thing called for. So I can do this, right? Okay. That program does not at all work the way you think it does. Not even remotely. What do you think that is? You think that's a for loop that prints a value 10 times, right? No. For is actually a lambda, and each is a higher order function. But when a teacher says, do you have for loops? We say like, no, we don't have, let me explain. And the moment you say, let me explain, they're like, oh, fuck, this is going to be one of those things, right? Now, when a teacher comes and says, so this Pyret, I haven't heard of it before. Do you have like for loops? Like, of course, here, I write this program. They're like, oh, good. And they never use for loops because none of the curriculum ever mentioned them because they're not even for loops. They're just for. It's just like lambda, okay? But it's like, like making a language that people will accept is like basically telling all kinds of lies that they want to hear. Right? Racket was very uncompromising about that before. Pyret is very compromising. There's a new Racket called Rhombus that is also compromising in the same ways.
That should be a code actually. These are all the lies that people.
Yeah, I can't say that in public, man.
So you are executing the code on the main thread, right?
Yes.
For Pyret?
Yes.
So have you?
B thread.
Yeah,
Only
the
thread, yeah.
So have you explored the service worker threads? Which
Yeah, because we can't get any data back and forth, right? The whole point of them is like you can do post messages and stuff like that, and it's just.
So there is a lab called Party Town which does that.
Oh yeah, I'm sure it's great. Yeah, no. Hey, look, here's the problem, right? Every 3 years there's some new JavaScript technology, and like we have a working language. It works great.
I thought you eliminated it for some code.
Yeah, no, we have been talking to the WASM people for several years now.
That was an
We have been talking. I mean, I know the WASM people really well. We've been talking to them. They know about our problem, and it's been a 5-year open issue to get some notion of continuations in there. And now they look like they're about to get composable continuations. So in principle, in about a year, we could rebuild Pyret all over again on top of WASM using plausible continuations. It's also like, you're all software engineers, so you understand, like, if you have something that works really well, like, where are you spending your time on?
I thought you eliminated it for some reason.
Yeah, it just, because we need shared data, right? Like, otherwise, if I have this thread that I can't completely control, like, we don't have a lot of like that. It's good for like long running computations. We don't have a lot of those. Good. Okay, error messages. Anyone want to hear about error messages? Yes. Error messages? Yes. Okay, let's talk about error messages. Okay, so here's what happens. Okay, so I told you about language levels, etc. So when a student writes this very basic beginning student Racket program, okay, it turns into that. Okay? And it's got all kinds of weird stuff in it because that's how it's able to give a good user experience with all the, it captures all the possible things that students can do wrong, captures them and gives you errors for them. Okay, so I talked about language levels. One of the things we want to do is also modify error messages so they only use the vocabulary of what you have learned at that point in the course. Okay, we had this experience when back in the 90s, Matthias and I went to visit a high school classroom, and some poor student, they're doing C++ in first like intro CS, so you can imagine how well that went. And some poor student had written something like, she had basically written like wage times hours equals salary. So it's perfectly right. You just, you have to put it in the left-hand side, right-hand side, and it was like made sense. Like it looked like a math formula, so she wrote a math formula, and she got some error message in terms of L values. Now you, of course, like, star on the left-hand side, L value, right? The student had no idea what's going on. Student calls the teacher has no idea what's going on. And basically now the whole classroom is broken down because like everyone's like, well, no fucking idea what's going on. Like, what is this, right? Okay, so what was the fundamental problem there? It's not with what the student wrote, it's that the word L value should never have shown up, right? Now, of course, as a language level, you could have said the left-hand side, it should have just said, look, left-hand side has to be a variable, it can't be an expression, because you don't know what to even do with an expression on the left-hand side, right? But even setting that aside, the word L value should only show up after the curriculum has introduced a notion of L value. Okay, so that's what I mean when I say that the error messages have to they have to be like epistemically closed. Okay, so this epistemic closure is a really important principle, right? You want to design with epistemic closure. So let's talk for a moment on what's the goal of an error message. Why do we give error messages? Why do we give error messages? Anyone?
Debugging.
Sorry?
Debugging for using.
Debugging, okay. Anything else? For understanding. Understanding, anything else?
How we differ, how the machine thinks differently than
how does the machine think that's different from what your mental model is of what the machine is doing? Anything else?
how to rectify it.
How to rectify, hopefully how to rectify also. Okay, so there's actually more going on. Okay, all of these are accurate, but there's also more going on. It helps you understand something about the vocabulary of sort of computing, right? There's this important principle in sociology called legitimate peripheral participation, which is the way people get into a discipline of some sort, is they always start off on the outside and slowly work their way in. Right. The great example that Lev and Wegener give is, how does somebody become a mechanic, right? So there's this person and, she's interested in cars. And so what does she do? You can't just become a mechanic. She goes and like hangs out near a auto shop, right? And then at some point, somebody's like, here, hand me a spanner. And she's like, this thing, like, no, not that thing, the other one, like, oh, and now she's learned that's what a spanner is, right? And after she hangs out long enough, somebody says, do you want to take a peek underneath? She's like, yeah, I'd love to take a peek underneath. And then that's how people become something, right? Through this process, right? And they start off at the periphery and then slowly move towards the center. And they form what's called a community of practice. And part of that process, that sociological process, is also learning how people talk in that community. They have their own language. They have their own words for everything. They have a particular way of talking. And you know this, right? You watch like a TV show, like detectives always have some vocabulary. There's lawyers use some vocabulary. And there's that process of learning it. Error messages are one of the ways we teach that vocabulary as well. We teach the vocabulary of computer science. Sometimes they enable participation. We have teachers who actually use the Pyret error messages, so I'll show you in a moment, to actually get students talking about the process of learning about math as well. Okay? Now, in Racket, we spent a lot of time because of this thinking about error messages. And then so we started about 1995. I started working on the Dr. Racket error messages. In 2010, we did a study. Okay? Guillaume Marceau, Kathy Fessler, and I did a study. And we were like, this is basically the first serious user study of error messages in like a fairly widely used programming language in educational circles. And it was an utter disaster. It was completely humiliating. Okay. And so here's an example, right? So the student has written something, you don't need to read the details. The student says, okay, define, expected only one expression to the function body, found an extra part. And they're like, oh, okay, I know how to fix it. And the error message, even pink highlight tells them what to fix. They go, they start editing, and they edit, and they edit, and they edit, and they edit. And 10 minutes later, the student just gave up on this program and moved on to the next problem. Okay, this was one of the worst situations, but we saw a lot of things like this. So we said, okay, what's going on? How well do error messages work? In what ways do they fail? What even makes a good message, right? These are fundamental questions we should be asking. Now, there's been a little bit of literature on this before, and typically when you looked at the prior research, it tended to do one of two things. Like, you would basically ask students whether error message is helpful. Oh, like, what are the students going to say? Like, no, like, there's no choice. Also, like, you know, if the professor wrote the IDE, they're like, well, I'm probably going to say, yeah, I know what answer he wants to hear. Right? So that's not very useful. Or they would look at things like, you know, the grade, like, did the grade change? Well, there's 10,000 variables that determine whether your grades change. Error messages are actually almost certainly not the cause of it. Right? Also, because in the US system, you can drop a class. So all those students have dropped. So of course the grades will go up, right? So hey, error messages, right? So in fact, error messages, crappy error messages are a great way of improving grades, I guess, on average, for who's left, right? So here's what we did instead. We said we are going to grade the error messages. What we're going to do is we're going to do deep surveillance. We're going to take all the keystrokes, and then we are going to look at the edits that students make in response to an error message as a way of grading the error message. Okay, so we're not going to blame the student. We're going to blame the error message if the edit is not good. Okay, so basically there's a sequence of executions. At some point there's an error message, and then there's additional keystrokes after that, and we're going to look at the student's response. Okay, and we came up with this what's called a code book, right? And we basically found that roughly 5 kinds of things that happened. They, ideally, there's some evidence the student has understood the error message, is trying to take appropriate action. Sometimes they do work that's unrelated to the error message, but it also, like you see this, right? You see an error and then you start looking at the code, you're like, oh, let me fix that thing up over there. Sometimes work is unrelated to the code. Sometimes it fixes the approximate error, and sometimes it delete the whole code entirely, which is not entirely a bad thing, right? So sometimes that's okay, right? So we came up with this code book. Now, you notice if you look carefully, right, there's things like, though perhaps not wholly, though perhaps not well, though other cringing errors may remain. Cringing, where did this word come from? Like, what's going on here? So let me tell you a little bit about how this kind of research is done, okay? When you are doing qualitative evaluation, one of the principles is you do not want only one person to do qualitative evaluation because they might not pay attention, they might be biased, they come with, et cetera, et cetera. Okay? So good qualitative evaluation requires multiple people to rate things. So what happens in this case? Let's just say we have a binary rating, right? So rater 1 looks at all of these sequences, says good, bad, something like that. Rater 2 does the same thing. And what you would like, of course, is that they agree as much as possible. Right? So in this case, about 80% agreement, right? Looks pretty good. There's a total of 10 ratings, 8 of them are the same, and one of them they different, so 80%. That turns out actually to be not a great metric because it can be too high because of just chance, right? Like in this case, binary, right? Flip a coin and you'll only get 50%. So there's a thing that's called the Cohen's-Kappa formula. So what you do in Cohen's-Kappa is you look at the observed agreement and you essentially take away the agreement by chance, right? So in our case, if you look at that previous thing, you actually get like 0.52, not 0.8, right? And you really want to get to about 0.7, 0.8 by this scale. So it took us about 2 months to come up with those 5 codes, okay? And to come up with 0.84. And that's where all of these funny phrases come from, right? Like things like, we'd be like, this person fixed the proximate error, and the other person like, but look at the rest of this code. There's like an error there. Oh, okay, so fixes the proximate error, though other errors might remain. No, but look at that. That error is so bad, I refuse to give this code. Like that is the negotiation that happens. And eventually you're like, okay, though other cringing errors remain, now finally we can agree that this is the code you want to apply, right? This is the process by which you do good science and this sort of thing, right? So 2 months, it's like 2 months to come up with this is just like 2 months of my life I won't get back.
You also factor in warnings?
We don't have warnings. We have only error messages. So, I mean, it is actually a very interesting question about what to do with warnings. Should a language have warnings? That's a research question for which I don't have an answer.
Okay.
Yeah.
At one point in time, the curriculum has to introduce the concept of L value, right? So how does the language enable it to introduce the concept naturally?
So I would argue that it's not the job of the language to make that decision. That's a curriculum designer's, that is curriculum design, right? You decide when you want to introduce a particular concept, right? There's, in curriculum design, you have what's called a learning progression, right? So there's a sequence of topics and you figure out, and there's like a graph of dependencies, a DAG, hopefully not a cycle, right? So some DAG of dependencies. And in fact, what happens is we have these DAGs and we have to figure out how do we linearize a DAG, right? That's fundamentally what education is about. We come up with a DAG, we say we're going to go in this order. And once you've decided it, I would argue the only job of the language designer is to provide mechanisms like hashlang so that you can make the language match whatever your learning progression says. It's not for the language to tell you when to do things. Okay. So anyway, you take this kind of code and now you can start to analyze, right? So you can look, for example, here's a lab. There are 8.5 errors during the lab. You look at what percentage of errors were each of these different categories, how many of them are bad. And so you get like a bad count, right? Like, so out of 8.5 errors, you get like roughly 3.16 bad error messages in that lab, right? So you can do a pretty detailed analysis of this and you start to see like various things, right? You're like, okay, hopefully this number goes down, right? So it starts 3.16, 5.51, which is pretty bad, 3.07, 1.7, 2.7. So it's going down a little bit. Of course, students are also getting more used to the language and making better edits in response to the same errors and so on. So that tells you something. Within a lab, you can see like what's going badly, what's going well. And sometimes some funny things happen. So like, here, like students seem to be having some real problems here with syntax definition and like, function calls. And you study the code they're writing and it looks like there's some vocabulary difficulties. Sometimes you see very strange things, like 5 weeks into the semester, students are suddenly making argument count, like they're getting the number of arguments wrong. Like, how is it that they manage 4 weeks to not make these mistakes and suddenly they start making mistakes? Well, it turned out, you look at the curriculum, that's the first time they were dealing with n-ary trees. And n-ary trees means like suddenly now there's the potential. Am I passing one argument? Am I passing n arguments? They get confused about that, right? So it's also a diagnostic about the curriculum. This one was super weird, right? Unbound identifiers. In week 6, they're suddenly making a large number of unbound identifier errors. You're like, what the heck? Like, is they like, how, beginners getting unbound identifiers, like, how does that even happen? Well, it's super strange. What happened was there were 2 parts to the lab that used very similar names, but not exactly the same name, and they were getting proactive interference. Never have found this otherwise. You look at the data, you're like, oh shit, you don't know how to write labs, right? So you learn other things also about the curriculum when you do this kind of analysis. Let's talk about vocabulary difficulties for a moment. We also interviewed students, okay? So interview. Their message says the function body. Do you know what function body means? Nah, the input, everything that serves as piece of input. Actually, no, it's this. When Dr. Scheme says function body, it means this part. Ah, man. Okay. So basically what we realized is we have these very careful error messages, right? Like define, expect only one expression, function body, found at least one extra part. What the student reads is basically this. Yeah. This goes back to that peripheral participation. We know the vocabulary, they don't. So we did the following study. We're like, okay, here's what we're going to do. We're going to give you this program and we're going to say, circle an identifier in this program, right? If you circle that, that's good. If you circle that, pretty bad, okay? And so we did this across like a large chunk of vocabulary and gave them various programs. Oh man, this was so bad, so bad. Basically, here's the results across 3 different institutions. Most of these, they barely got 50%. Basically, they didn't know any of the words in the error messages. right? And it turned out there was actually like a kind of serendipitous control that happened that I'm not going to get into. That was super funny because what happened was places that professors had reinforced the vocabulary, they did better. Where the professors had not reinforced the vocabulary, like with more experience, they got worse, right? Just like not what you would hope for, right? So basically error messages use prose and prose is hard. And we had also we'd done this very painstaking thing for 15 years where we had carefully split apart the vocabulary, like, you know, where it would say a function, we're like, sometimes it's a constructor, sometimes it's a predicate, sometimes it's a selector. We built all of these. And basically all these refinements we had done had actually made things worse. And so we went, like the most painful thing I've done in my life, we undid 15 years of work and turned all these back into function, right? And a whole bunch of things like this. So what Pyret now does is a little bit more interesting. Sorry, where am I? Here. So here's a function of 2 arguments. Can you all see the code there? Yeah. Okay. And so now if I say f of 1, 2, 3, what it does is it's very colorful, okay? But you can actually click on the word arguments. You can just hover on the word arguments. So you don't have to know what the word argument means. You can learn the word argument from the IDE, right? So it's like 3 arguments are passed to the operator. What is an operator? Well, that's what an operator is, okay? And this is the definition of the function, and it accepts 2 parameters, right? So all of the pieces are basically like, you know, these hyperlinks and mouse over and so on. So you don't have to know the words. You can even learn the words, but even if you never learn the vocabulary, you still have an understanding of what's going on. You don't have to know the vocabulary beforehand. Okay? So that's this principle we follow. And, you know, Apple famously wrote these things called the human interface guidelines back in the 80s, starting in the 80s. And so we have now a human interface guideline for designing error messages, because the other thing that happens is it's not just languages, it's also libraries. And so language, you can sit there and fix all the error messages in the language, and then your library author will come along and make up their own separate rules, and you end up with inconsistencies there as well, right? So you actually, like every programming language, needs these sort of error message guidelines to decide what they should be. And there are things like, you know, frustrated students will peer an error message for clues. You have to avoid offering hints unless you're sure what's going to happen. There's a structure, there's a form, there's a vocabulary, what words are permitted, what words are not permitted. So we, for example, never use in Pyret and WeScheme, we never use words like abort, right? Because especially in America, it's a very, very touchy topic, right? So you never abort a computation. You can terminate or stop a computation. You don't abort a computation, right? So we do, and you have to take those kind of cultural factors into account when you decide. Okay, and also, you know, we took all these words and merged them down into simpler concepts. So this is part of like pedagogic language design, right? Like in some sense, every language needs a vocabulary guideline for how to design our messages, right?
So coming from the other side, the industry, like Elm is probably the first language that really took error messages into, you know, and then that affected how Rust started doing error messages.
That's right.
So, I mean, is this kind of...
We've had great conversations with both of those teams. Okay. Oh yeah, for sure. Yeah. I think they've read at least some of our papers. So yeah. And I've certainly talked to Evan about it, and we've talked to the Rust team about it. I mean, Rust absolutely does a lovely job. I would still like to do some studies to find out, make sure that job is as lovely as it seems to be, right? Because again, we're looking at the lovely job through the eyes of experts, right? And what you learn is that's not there's a whole concept in education called the expert blind spot, and we all have it. So. But no, I think both Elm and Rust have been great in that regard, and I think they're also forcing every other language to up its game, which is great. Yeah.
So do you have any statistics like on how many people make errors due to using a language feature that has not yet been introduced to the students?
Yeah, that's a good question. I mean, in Racket language levels, by definition, there can't be any such errors.
So the thing that I'm wondering is that if the error messages are that good, maybe you don't even require these subsets of the language.
No, because it's also semantics, right? I mean, the thing that can happen is you can write a program that is not syntactically erroneous, but does some weird semantic behavior. We have several of those examples too, right? And so the program runs and it produces like 0, and you're like, why did it produce 0? well, see, you didn't realize that this thing actually means that other thing. You haven't seen this language feature yet, but it actually does this other thing as well. And we hadn't shown it to you. And I have to explain how that works. And that's what's really going on. Okay. We document some of these in the paper. Yeah. So it's not just errors. It's actually, errors are great because errors, at least the program stops. You're like, I don't know what the error message means, at least the program stopped. It's much worse when the program runs to completion and produces an answer where you're like, I can't possibly explain how this syntax produced this answer.
Okay.
Much worse. Errors are good news. Yeah.
Just an anecdote. So my friend who is a PhD at MIT, he was trying to write a C++ program. There was an issue there, and
yeah, he was trying to write. You already told us you're trying to write C++ program.
So of course. so when he ran it, it compiled and then it gave a seg fault. So he was like, I'm happy now.
Yeah, no, seg faults are great. Seg faults are the best possible news because it produces 17, like, I don't know. That could have been a memory address. That could have been an answer. That could have been like memory address minus some other answer. Who knows? No, seg faults are great news. Totally. Yeah. Let me see. We're starting to run out of time, aren't we? I don't want to go into this in too much detail. Yeah, I don't need to talk about all this. Let's not worry about all this. Yeah, that's really what I want to say. Like, let me just summarize. Okay, so here's the thing I want you to take away. Student programs have a lot of issues. Okay, first of all, they contain all these media. That's a good thing, but that also causes issues for, like, you know, language design, runtime design, and so on. You really want student programs to not modify the state of the IDE. That causes, but at the same time, if you like have to keep spawning processes or spawning like VMs, that comes with costs. You have to think about that. You want student programs to be graphical, but you have to deal with like event loop interference and so on. Students are terrible at managing resources. You don't want them to be good at managing resources starting out. That's not usually the thing we're trying to teach them. They will not handle exceptions. They don't know about exceptions. It's your job to make it graceful. And finally, they need, like, you know, good error messages, not a good feedback, et cetera, et cetera. I'll quickly show you a new thing that I haven't demoed this before. But so this is a new IDE interface we're working on called Parley. So let's do something like this. Actually, that's too big. So let's go back. Let's say I want a rectangle.
Oh, it's Harley with an ARR.
Parley.
Harley. Oh.
Yeah. Okay, and then actually let's do this. So you notice I'm sort of making mistakes as I go along, but I can keep re-editing, right? So it's kind of like a notebook-like thing, but for beginners, right?
It looks like a chat interface.
Can you show an error?
Exactly. So I can do like okay, and so now let me give this
Hey, isn't this basic? Isn't this like basic?
If you think so, I will take that as a compliment. Okay.
I have one thing. Basically, we talked about parameters and exceptions, right? So what if students like learn by making mistakes, and what if you pass the less or more parameters? Say, for example, rectangle, right?
Yeah.
You might have provided height and width, right?
Yeah.
What if I pass 3 parameters, some mistake I did, okay?
Yeah, like this.
As a student, a beginner, yeah. So how will the response will be? How will, like in this way, how will the response will be?
I mean, that's what I just showed you, right?
Okay.
No, that's exactly what it is. This is the IDE. This is the honest goodness running IDE. Okay. It's not a demo. Yeah. Okay, so anyway, yeah, this is just a new interface we're working on. It's basically this principle of chat, but we're trying to figure out like a thing that's somewhere between a chat and a notebook and all these other things. And you can also like, you can go in here and you can change the view to be different things. So you can say, I want to show this in different ways, get shareable links, blah, blah, blah. So it's this new interface we're working on. And it's a kind of little playground for trying out new things.
So basically, this is a REPL for Zoomers. With history.
Not for us, man, not for us, yeah. So anyway, that's what I talked about, and that's how you can reach me, and I'm happy to take other questions. Questions? What do you want to know?
Pyret statically typed or dynamic?
Well,
Like if it is dynamically, why did you decide to go?
so in Pyret, you can decide which one you want. There's a good question. That's a part of me that is very deeply I grew up on Scheme, dynamic languages. I'm cool with that. I've also built type systems for JavaScript. I built type systems for Python. I have done the formalism of Java's type system, type soundness. So I sit completely comfortably on both sides. Okay. I do think that there's a lot of value for beginners to not worry about static errors. Because essentially now they're trying to understand one system, and you now force them to understand two systems, and they're not exactly the same, right? I mean, there's as a PL researcher, I can tell you, oh look, you get coverage, you get this, you get that. Like, oh, you look at the branch that was not taken, and you don't have to worry about it. But explaining to a beginner, like, why is the case if I say if false something is going to give a type error, but I said if false, like, because they're just about getting used to the dynamic semantics, and now you want them to understand a static semantics as well. That's a lot of cognitive load.
Even while they're learning it, they would still be writing statically type safe programs, right? Generally, while you're teaching, you wouldn't.
Maybe. Right? The point is dynamic errors are much easier to explain, right? Like you make the error, you say, okay, what happened? How did this value get here? Everything is explicable in terms of the notional machine that they're trying to learn, right? After a while, it makes sense to say, okay, but it's also super frustrating to get this error when it could have been caught earlier, right? I like to think about introducing type systems as a way of saying, aren't you annoyed? Aren't you mad? Like, what is this? Like, why do you have to discover this? How do you have to run the program and find this out? Wouldn't it be nice if we could find this out without ever running the program? That is a great time to introduce it. And that's exactly why we have this type checking option. At some point, you say, let's migrate to this other option instead. The other problem is it is very difficult to build a good type system for various things, right? So a lot of what we do in Pyret is we do a lot of programming in the data science curriculum with tables. Getting a good type system from tables is super hard. I would say it's like an open research question. I've done like whole grad seminars on type systems for tables, right? And we read like every available paper and said, yeah, not there, nothing we can implement yet, right? Because you need like all kinds of like, you need weird kinds of polymorphism, blah, blah, blah. It's a whole like type theory talk that we could talk about there. I just don't have it, but I need to teach data science to sixth standard students using tables. Like that's the obvious way to do it. It's the best way to do it. And if the type systems aren't there, that's just too bad. Like I'm still going to teach the curriculum, right? So in some sense, there's also some big holes in like what type systems have been able to do. That's a problem for us.
So what are the future plans for this? So for language, what is the next one roadmap? What are you doing?
So Pyret is a very unambitious language. We want to do no research at all, right? Because every time you do research, like two things happen. First of all, you waste time writing papers, okay? And every paper is like 3 months of like non-language implementation effort. The other one is you get some idea into your head about what's going to be really cool about your language, and then you make that like 100 times better, and you neglect all the rest of it, right? And so we are like an anti-innovation language. Right? We do not want to do anything that is not fairly well understood, like type systems for tables.
So let's go.
Huh? Yeah, we're like the Go of like PL, but we're okay with polymorphism. we also have some standards unlike Go. So yeah, no. So I mean, I do other research like formal methods and stuff like that I'm happy to talk about. But here it's like it's all about curriculum. It's all about curriculum, pedagogy, outreach, getting it out there, supporting thousands, tens of thousands of students and stuff like that. And then you can't really innovate very much. Like the language is most.
So you would say that it is sufficient for curriculum also?
More than sufficient. There's some tweaks here and there, and I'm working on some small things, but we argue about what small changes. But I think for the kinds of things we are trying to do, where we're trying to teach like basic data science at scale, we're trying to teach better math using programming, we have most of what we need, right? The language concepts are there. I think what we could use a lot of work on is IDEs, right? That sort of thing. Like thinking about the user interfaces rather than language concepts themselves. Now, like we could talk about like block interfaces and stuff like that, syntactic thing. But again, I think of that as like an IDE syntax thing rather than the language itself. I think, core functional programming with a little bit of like state is like, that's all we know. We've had it since 1972. I don't know what to do. Other questions?
By the way, was Shopify also like part of the same effort of Pyret, or was it made independent?
It was basically, after we built Pyret, Arjun had this great idea of saying, like, why don't we just extract that idea, the core thing that's in the Pyret runtime system, and extract it and just make it like a much more general idea that everybody can use. Well, I was like, well, how do you do that? He's like, well, if we just made it a JavaScript to JavaScript compiler, then anybody who uses JavaScript can use it. So that was, yeah. So it's sort of an outgrowth of Pyret, sort of a sibling of Pyret. Other questions? Yeah.
Do you think that multi-thread programming should be taught in schools?
I don't know, man. It's like, I'm not going to say that. I think it's like, it's depends on who you're teaching and what your goal is, right? Like there's some goal you're trying to achieve. Like when I go to middle schools, so we want people to learn some computing. I mean, I'll avoid giving you a whole talk on this, but we want people to learn some amount of computing, okay? But you can't add more to the curriculum. It's already full, right? It's not like everybody is sitting with a wide open slot saying, oh, for 100 years, there's a big gap in the curriculum. We have an hour to fill, please come. Now we have computer science, right? But school, like even when I went to school curriculum was quite full and, we didn't have computer science back then, right? So how do we get computing into schools? Well, you have to throw something out. What are we going to throw out? You can throw out geography and turn Indians into Americans who don't know any geography. History maybe could use some improvement, but the point is there's not much give there. And then we're like, oh, no, computer science is an absolute priority. We're going to add computing schools. And we're like, that's not going to work because 5 years from now, there's going to be a new thing. Sure enough, 5 years later, data science for all. So what's data science for all going to supplant? And now 5 years later, AI for all.
Right.
So what's that going to supplant? That's never going to work. You can't keep throwing things out. At some point, you run out of things to throw out, right? So our strategy is instead what we call integrated computing, where we take disciplines that already exist and teach limited amounts of computing in those existing disciplines, but in a way that makes sense for the discipline and still meets some kind of computing goal, right? That's this thing that we call the Bootstrap project, right? So in that setting, multi-threaded programming doesn't fit, right? Is it math that's going to teach multi-threaded programming? Is it civics that's going to teach multi-threaded programming? Well, it could be anything as long as it made sense there. I haven't found a way for it to make sense, right? You could say, well, images don't fit either, but images are actually super powerful for us for teaching function composition. Tables don't fit, like what is SQL doesn't fit, but tables as a concept of data, as a way of teaching a data-enabled history or civics curriculum does make sense, right? So maybe there is a way of thinking about multi-threadedness as well, if you can make it fit the curriculum goals of some existing discipline. It's not something I have found. It's also not something I've searched for, but could be.